you, Sophia, for the warm introduction, and thank you for
이스라엘 영상이
take 2 slides after
이스라엘
my
영사라.
presentation. I did it
브라이트웨이가?
already, because
브라이트웨이비전.
already introduced what is gated imaging. So just in 2 words, gated imaging is an active system, as Julian said. We emit a very short pulse of light and collect the reflections. I'm not going to explain what gated imaging is, because, as I said, it was already explained. But if you like, we have a demo card, and you can really see it in action. And my colleague Ayelet will show it in the evening in the car, so you'll be able to enjoy it firsthand. What I'm going to talk about is first to share with you our view of the current situation of ADAS and imaging systems. I'm going to talk only about cameras, not about radars and not about other sensors. As we all understand, the automotive requires several sensors. I see it like our human being, we have several sensors. We are not relying on a single sensor. We are accumulating information from several sensors. Then I'm going to share with you what we see as the industry need, what needs to be improved. And then I will show some updates about gated imaging, and not only at night. And I understand the QA is in the end, so the QA is not in my presentation. And what we see today is some limitations to the current, I would say, visible sensors. I don't want to use the word RGB because some of them are not RGB, some of them are clear, or whatever combination that is used. And they have some limitations. The first one is noise. We'll have a slide in a minute. And you have some limitation. Usually when you have problems with noise, you can make a longer integration time, but this is not something you can do in automotive. In automotive, you have to do a very short exposure time, otherwise the image is blurred, and you don't want to blur the image. Background, target to background is something that has to be improved. Some of the targets have the same reflectivity of the road, some of the targets have no reflectivity. For instance, a specular object on the road will not reflect any light, and you have to know how to deal with that as well, because it poses a danger to the car. Dynamic range in entrance or to exit to tunnels, and also when a car is coming in the opposite direction. So it's not enough to have a very sensitive sensor, because then it will be bloomed when a car will come in the opposite direction. You have to do something a little bit more complicated there in order to solve this issue. And of course, backscatter, but this is true for active systems. Most of the audience here is dealing with illumination systems, so active systems, so we all suffer from backscatter, which is the reflection which is coming from the aerosol particles in the air, or from, if it's dust, you have to deal with it. So just to make sure that we are on the same page, when I say noise, each sensor has a noise floor, and below that, the signal to noise, we like to measure that quality as SNR ratio. Below that, you will not get good detection. The figure of merit for a good detection is above 10. You can live with 5. So there is a threshold at 5. You want to have a signal to noise better than 5, otherwise the image is useless. And as I said, backscatter is one of the limiting factors. Also in automotive, there was the talk here before me about street lights. They also sometimes degrade the image, because if you have a street light and you have an atmosphere full of aerosols, some of the light from those aerosols will be scattered into the line of sight of the sensor, and that will reduce the contrast eventually, as you see in the bottom image here. This one, the bottom image. Actually, there's no problem of signal to noise here. There's a lot of light, a lot of photons, but they're not coming from the right location. So if you look at the upper picture, so you have an active system. It illuminates the target. It also illuminates those aerosol particles, and the idea is to differentiate between the two. And you have also the street light, which also reduces the contrast. And these are the contribution to what you're sensing eventually all together. We call that the phenomena of the street light, which is coming into the line of sight, we call it air light. Taking all those limitations that I just described, And looking at practical results today in the field, we see that at nighttime, ADAS is not as effective as it should be. And there is a lot of room for improvement. We are seeing now a beginning of an interest to solve the issues of nighttime, but there is not a strong demand from the industry yet, but it's keep changing now, and we see an improvement in the attitude of the industry. And if you look, for instance, in AEB systems, it turns out that only 32% of the time they are effective. This is a study by the Insurance Association in the United States. And this is why we also share a slide about AEB using gated imaging. And let's go on. So now that we saw that we have to improve the nighttime, let's see, what do we need in this? What are the requirements for a nighttime system that will work properly and will solve and will decrease significantly the number of casualties at nighttime? So first of all, you need, for large objects like parked cars, large obstacles on the road, you need a very long range, at least 250 meters, in order to also detect curves on the road far ahead, so you're not surprised. You have to sense lost cargo. These are small targets lying on the road at a distance beyond 160 meters. Definitely you have to work at low light visibility and in harsh weather conditions. Maybe this is where you mostly need the assistance of the car, if you like driving like me. Range discrimination is very good in order to increase the contrast. If you can take the target out of the background, that would be very helpful for any algorithm. And I'll show some examples for that. Dynamic range, when you exit or enter into a tunnel, I think that entering into a tunnel is more dangerous. If you don't see what's inside and there is a car that's parked into the tunnel, you might hit it from behind. Retro detection. Cars, it's mandatory, all cars have lighting community, you all know it. They must have retroreflectors at the back, the rear end of the car. Let's use it. Also when the car is not driving, also when the car is standing. And of course, it was discussed several times here, low cost. So when we look at this issue of low cost, we always look, what can we replace in the vehicle? And the gated imaging, as I said, it's an illumination system and a camera. So with the camera, we're looking to replace the tele. We saw some presentations today about integrating sensors in headlamps or in other locations. So we are looking at putting our camera as a replacement for the tele camera. So the incremental increase in cost is not significant. And to put our laser emitters as part of the daytime running light or the part of the fog lamp, whatever the designer eventually thinks it sees fit, because they can go anywhere. And that saves cost, the incremental cost decreases because you replace other parts. And this is the way we do it. So let's see, when I say looking at the long ranges, let's see an example. So in this example, for instance, you want to see the curve. You want to see that the car is coming. You want to see that the car is coming in the opposite direction relative to a high-end. This is a 12-bit RGB camera, so it's quite good. And you want to see the lanes. You want to have what we call situational awareness. We as drivers, but also as sensor system, we need the same thing. Now it's a different requirement if you design a sensor for vision, for human vision, or for machine vision. Machine vision they have a different requirements, so you have to fit your sensor for that. In terms when I say range discrimination, and this is one of the advantages of gated imaging, is that if I can take the background out and just see the range that I'm looking at, and this can happen very fast. So you're not losing any information. You have the full range, but you also have what we call a slice. You're able to improve the contrast significantly. So this is just one example, and that will improve the detection significantly because you don't have all the background. You don't care what she's wearing, you don't care about what's behind her. You will always be able to see because of this range discrimination. I was stating lost cargo, so this is an example, a few examples of cargo, a brick, a woody piece, a metal rim. So the metal rim might be detected by other sensors like the radar, but those targets will be difficult to detect by radar, especially if they're also not moving, so it's another problem. And if you look at the image coming from the gated vision, definitely you see them. Now, as was said before me, this is positive contrast. So the targets reflect more than the background, especially in this case where the road is wet. So it's like a specular reflection which is coming from the road. You don't see anything coming back to the sensor, but you see the targets very well. So what do you do in those situations? What we do in those situations, we detect the shadow. And we call it shadow detection. So you're actually able to we have two illuminators on the car, one on the left side, one on the right side. We have the camera installed behind the rearview mirror. So you have the overall scene. This is taken by the two cameras, the upper image. So you have a target, and if you do it clever enough, you can modulate the left illuminator and the right illuminator. This happens, our sensor works at 120 Hertz, so you're not losing any information. You can do it fast enough. You can operate at one time the left illuminator, at one time the right illuminator, modulating it and feeding it into an AI system will definitely recognize those shadows, as you see here, and they're moving from side to side as I modulate the illuminators. And this is an information that you know, A, it's not paint on the road, B, it's something standing out, and this is also very helpful if you have none or similar reflectivity from the target as from the road. So combining all this together, you can develop a software. In this case, it's a neural network based, but it's not a must, that will detect the targets. It might not do the classification, but definitely will detect the targets, combining the shadow, the slices, and everything together. Now, I'm showing here the daytime images, also when I showed the range discrimination. And the reason for that is that with gated imaging, it's much more complicated at daytime than at nighttime. So I'm showing you the extreme case, not the easy case. The easy case is at nighttime. At nighttime, it's easier for a gated system. We said that the system has to work also in harsh weather conditions. So this is a video which is coming from the north of Sweden. And you see three sensors here. The gated vision, the visible HDR sensor, and the thermal imager, the bottom one. So as you see on the gated vision sensor, I'll play it again. As you see on the gated vision sensor, you can estimate the range by the number of posts you see on the side of the road. You have situational awareness, you see the power lines, you see everything versus the visible camera. You are significantly affected by the backscatter, and the range is limited. You might see 1.5 posts versus the gated vision where you see a long range. So this is another example. Exit and entering a tunnel, that was already said, so I will not go into it, but the nice thing about gated imaging is that you are not dependent on the surrounding illumination so much. You are actually controlling the scene. You're controlling the scene illumination with your very short pulses and a narrow line width that the camera works with. I'm showing here an example also at daytime. At nighttime, it's much easier for gated imaging. The scenario is that the car is driving. You actually see here three images. It's very hard to see them because it's at 90 Hertz, this specific frame repetition. And what you see here is one, an active system. It's an active image. It's an image that I took when the laser is active. The second one is a passive image. It's the same exposure time, but without the laser. And the third one, and this is just for the convenience of seeing the benefit of it, is the subtraction of the two. So what do we see? If the car is far away, and you don't have any issues with it, the closing speed is okay, you don't see any issues of running into it. By the way, this is the active system, and this is the passive system, the passive image, and this is the subtraction. So you still have information about the lane mark, so you know if you're detecting something where it is. The image is quite similar to a regular visible image. So normal algorithms that work with visible cameras should work very well with gated vision images. So this is the subtraction. This is what you get when you do it when the car is not in your interest range and not in the interest closing speed. If I go closer to the car, and now I have an issue, I need to create a warning. This is what comes out from the sensor. These are the two images again. Now you have here some reflections from the target, because again, the gated imaging, as was explained very well by the speaker before me, Julian, images only a slice of the range. It does not, you can control it. You don't have to image the whole range, and you do some range discrimination. And then you get this reflection. You get also the retro reflections, very significantly, but also the diffuse reflection from the other parts of the vehicle. And also if you have a specular vehicle or a specular paint on the vehicle, some of it will always return because we have flood illumination, the whole scene, we are not detecting specific points. And this is just an example for A/B, because as we saw that there is a need for improvement in that field. And this is another slide I borrowed from Julian. And this is actually, I don't have to say what you see because it was already explained. But what I want to say about this slide is that most of the industry is using the regions where you have less sunlight. It's good, especially for active systems, because you don't have to cope with the background. So your signal to background ratio is very good. But if you look at the reason for that is that water particles are very absorbent on those specific lines of the spectrum that we see. Now, if you want to see in high humidity, in rain, in fog, so maybe it's not a good idea because, as we said, water particles are absorbent in those regions, so you have to look for other regions. So this is one consideration you have to do when you consider the wavelength. Scattering is another issue. Scattering, when you go to other wavelength, scattering depends a lot on the particle size. And as far away you are from the particle size, it's better. So this is another consideration. And of course, if you want to be mounted inside the windshield, it's another consideration. One more consideration is the quantum efficiency of silicon. As we said, cost is a major drive in our industry. So at the moment we see silicon as the only sensor that is able to meet the cost requirements. And if you go to longer wavelength, you lose the quantum efficiency that you require. We talked about lost cargo. In the lost cargo case, you need high resolution. So in this graph, what you have here is that the y-axis is the resolution actually, and the x-axis here is the weather conditions. The resolution actually is something parallel to the range that you will be able to detect a certain target. You can look at it at that. The better the resolution is, the smaller it is, the better the resolution is, the longer range you will achieve. So if you look at the radars, they work very well in all weather conditions, but they have very low resolution. If you look at LIDARs, they work very well at day and at night, but will not cover the adverse weather part, and have medium resolution. If you look at cameras, cameras have very good resolution, and if the target with autonomous or others driving is to achieve a performance slightly better than the human driver, that should be sufficient. And so the day camera works very well at daytime, but if you have already decided that you need a camera in your sensor suit, then you have to extend its performance to nighttime, and this is where gated imaging comes in. We supplement the day camera to the nighttime environment, and this is what we do. So, as we saw, we have an answer in terms of the right wavelength, in taking into account the whole requirements. We are not as sensitive in our dynamic range as a regular sensor because we are controlling the scene illumination. We can take care of backscatter. We actually look beyond it. We have this range discrimination, as I call it, in order to improve contrast and if you have low contrast targets, it's not low reflectivity, these are low contrast targets, you can use the shadow in order to detect them. By the way, we as human drivers, we do it, we don't even notice it, that we come to some conclusions based on other vision cues that we have as we drive. I'll stop here. I wanted to thank you, and you're all invited to the demo later on.
972가 이스라엘 번호.